And welcome back. This is AP Chemistry, and you're here with Miss Gray and Miss Mulholland. Say hi. Hello. And we're going to talk about the gas laws. So a lot of this is going to be a review from last year's general chemistry, and I think you're going to like it because you guys know this stuff. So the gas laws basically describe how things change when the variables change. So what are those variables that might influence the condition of a gas? What do you think? All right, you say them. What things might change it?
Temperature.
Okay, temperature. Right, a hot air balloon is called hot air for a reason. Okay, what else?
Pressure.
Yep, pressure. And?
Volume.
Volume, sure. And more?
What else do you think?
How about the amount of a gas?
Sounds good.
Which, of course, we measure amount in moles, in case you are wondering where that came from. It's moles, people. When in doubt, go to moles. That's the rule in our class anyway. So first, we're going to start with Boyles Law. The pressure and the volume, Boyles Law says, are inversely related at a constant temperature. So what the heck do we mean? Well, here's what we would do in math. An inverse relationship has some constant value when P and V are multiplied. But in normal language, not mathematical language, it says this: as one goes up, then the other one, for inverse, does what?
That one would go down.
Yep. So when pressure goes up, volume goes down. When volume goes up, pressure goes down. Yep, inverse. It's not that hard. So I want you guys to sketch a graph. I left room in your notes for you to sketch a graph to represent this kind of relationship.
Can we draw maybe what the relationship is? I mean, is there a way to draw
the formula?
The pressure and volume formula for Boyle?
There is a way. Shall we derive it from our graph?
That would be awesome.
All right.
Yeah. Let's do
First, yeah, we'll give now that they've had a chance to sketch the axes and everything and label them carefully, then let's draw a line. I'm going to predict that most of our students have drawn a line like this, because I said it's inversely related. So as the pressure on the x-axis is getting higher, wow, that's a good box, then the volume is getting lower. So I'm predicting that that's probably what our students have done. In reality, this is the shape of the graph that we see. So rather than having a straight line, it goes at a weird angle, like a curve. You may recognize this relationship where you know y is equal to m times x plus b. We didn't get a straight line, so we can't use the slope-intercept relationship. That's not very convenient for a scientist.
Right.
We don't have a straight line. Here's how to get one. This graph is of this form, y equals 1 over x. So we take what's on our x-axis and we do 1 over x. So 1 over the pressure is how we turn a curvy graph into a straight line graph. Yeah. We want to have a slope equal to some constant. When we graph the volume times 1 over the pressure, we can get a straight line. All right. So y equals mx plus b. Let's go back to that. This set of conditions where my volume and pressure describe this point on the graph. Then I have this other set described by a new volume and a new pressure. Then to make the relationship between the two, I need my slope-intercept form. Okay, it's a straight line. So my slope is going to be equal to y2 minus y1 over x2 minus x1. Only in this case, my x is the inverse, right? So it's 1 over p2. Oops, and that should be p1. Like my scribble job. Yeah, that's a p1 now. Okay, so since it's 1 over the p1 and the p2, then our constant is, if you take a fraction in the denominator, then it's pressure times volume instead of pressure divided by 1 over or volume divided by 1 over the pressure.
Right, copy dot flip.
Yeah, so we would express this as V1 times P1 equals V2 times P2. And that's Boyles Law. Is that what we had before?
That is what
Yeah,
we have.
that's what we had before. So that's what Boyles Law says. So all of these laws that we use come from the equations of straight lines, whether you're in physics or in chemistry or any other sort of law that you need a formula for. They come from the equations of a straight line. Now that we've done this once, we're not going to derive anymore. We're just going to tell them what it is. Sound good?
Sounds great.
Yeah. Deriving equations. How about we show how to use it instead?
I think that would be actually better.
Yeah, let's show how to use it. Okay, so in this example we have a given volume, 20.5 liters of nitrogen, which we all know is one of those Brinkelhoff elements, N2, and it's at a temperature of 25 degrees Celsius and a pressure of 242 torr, and it's compressed to 9.8 atmospheres at constant temperature. So since temperature is constant, then this I don't have to worry about. It's going to stay constant. Boyles Law says P1 times V1 equals P2 times V2. So let's identify what's what. What was my initial pressure?
742 torr.
Okay. And then my V1,
20.5 liters.
20.5 liters. And then P2 is given?
That's 9.8 atmospheres.
Oh, darn. So that's not very handy. And then the new volume is my target, V2. We'll put a question mark. So which do you want to work with, atmospheres or torrs?
Let's work with atmospheres.
All right, 60 torrs are in 1 atmosphere. So 742 divided by 760?
0.9763.
Okay, that could be a pressure in Falcon because we're always less than 1. Yep. Well, unless it's a high pressure system, but we don't usually get above 1. And we're going to find the volume. So we take our numbers and put them into our formula that's given here. So P1 is 0.9763. Don't round anything yet. We'll round at the end when we're looking at our sig figs. Times V1, 20.5. And that's going to be equal to 9.8 times V2. So to solve for V2, we're going to divide both sides by 9.8. AP Chemistry students rock at math. I don't have to show them all of these steps, but I still have to do all of the steps anyway. So, do you have the final answer?
2.0423. Or did you want more?
No, we're good.
Okay.
And that should be in liters because we started with liters, right? So it looks like we're going to take up a lot less space. We started at 20.5 liters and now we're at 2 liters. But that should make a lot of sense because our pressures dramatically increased, right? From 0.97 to 9.8, that's almost 10 times increased, and so the volume decreased by almost 10 times.
Right.
Okay, now let's look at sig figs. Here's our pressure, and here's our pressure, and here's our volume. So our initial measurements started off with 3 sig figs here, 3 sig figs here, and 2 sig figs here. So our answer is limited to only 2 sig figs. So 2.0 liters, and put a box around your answer, because that's the way I like it. Good enough. Let's go on to the next thing. Example 2. So now that we've worked this through carefully, we're going to take this one at a faster pace. Here's our volume, V1, 30.6 milliliters. Do you suppose we'll need to liters, or can we leave it this way?
Well, if our second volume is also in milliliters, they probably cancel.
All right, well, it is. So V2 is 750 milliliters. I'm not going to bother then converting. And then my pressure is at 740 torr, so P1 equals 740. I'm going to call this P1 because it matches my V1. And then we're supposed to find the final pressure. We'll call that P2. And Boyles Law, oops, we better say it the same way every time. P1 times V1 equals P2 times V2.
we're going to need to convert. Do we want to convert at the end, or do we want to convert at the beginning to kilopascals?
Either way we do it, we're going to have to do it. Might as well take care of it now, huh? Because the target says final pressure in kPa. So let's put 760 torr down here, and then we have 101.325 kPas. kPa. What do we get?
98.6586.
Okay, so we wouldn't round the number in our calculator, but I'm not going to write all the calculator vomit on the screen. Okay, we're solving for the final pressure, P2. So I'm going to take P1 times V1 and divide by V2. So P1 is 98.65, whatever else your calculator says. And I multiply by V1, 30.6 milliliters. I should be putting units in all the way along so I know I'm getting the right stuff in the end, huh? Divide by 750 milliliters. And milliliters cancels. So we're ending up for a pressure answer with units of kPa. That's a good sign. We want to get pressure. And what's your number?
4.025.
4.025. Does that seem like a reasonable amount? That's a very low pressure, huh?
Right, but the volume.
Okay, so we started at 30 milliliters.
Right.
And expanded.
Quite a bit.
Yeah. So for the pressure to drop quite a bit, makes sense. How many sig figs should we keep? We better check that out. Looks like I have 2 sig figs in this number, and 2 in this number, and 3 in this number. So again, we're restricted to 2 sig figs. Any students out there trying to count the zeros as significant? Remember, there's not a decimal place in here, so they don't get to be significant. I know, tricky stuff. All right, let's look at another law. Boyles Law we got, right? That one was pretty simple and straightforward, and so is Charles' Law. The volume of a gas varies directly with absolute temperature at constant pressure. So if the pressure is constant, then when it says it varies directly, that means when one goes up, it makes the other one go up too, right?
Yes.
That's our non-mathematical terms. Here's our math terms. If we're writing a direct proportion, then we put that proportion constant K right here. V equals K times T. Notice it says temperature has to be in kelvins because if we're going to be dividing by a temperature, we don't want to have a temperature equal to 0. Then we would have an answer that's undefined. Okay, our students know what to do. Sketch a graph to demonstrate this type of relationship where one thing goes up and the other thing goes up.
So what's the relationship?
Oh yeah, we wanted to do that before. We said we're not going to derive any more formulas. So let's just tell them.
All right.
V1 over T1 is equal to V2 over T2. Right,
So like if you heated it, you would
Right.
expect.
If
but
we
it
heat
won't
this
move.
up, we would expect our container to expand.
Right.
But since it can't, our pressure is going up instead. That's what we don't have control over, is a constant pressure. So here I can change the parameters. Let's set the pressure to be constant. Now we'll see Charles' Law in action because now we can have the pressure constant.
There we go.
Yeah. So now, let me close the volume up a little. And to keep that pressure constant, then the volume has to expand. Okay, here's a couple of different gases. And I wanted to point out that all of these gases may have a different slope because there's different interactions in the molecules, but they have the same intercept here, that they're all going to meet at the same point. And this is how we got the relationship to describe what 0 kelvins would be, because no one's ever actually gotten the temperature all the way down to 0 kelvins. But all of the lines in our graphs have met at the same point when they've been extrapolated down to negative 273.15 degrees Celsius. That's where absolute zero was predicted. And now at CU Boulder is where they come the closest in this super cold research. And that's matching pretty closely with they're getting a 0.000000001 kelvins.
Wow.
Yeah, pretty cool.
So that's a pretty important number to remember.
Yeah, especially for the next slide. Good thing that my AP Chem kids already have that number memorized, because now we're going to have to use it. You ready? What would the final volume be if 247 milliliters of gas at 22 degrees Celsius is heated to 98 degrees Celsius and the pressure is held constant, of course, because otherwise we can't apply Charles' law.
As we just learned.
Yes. So here's my law, V1 over T1 equals V2 over T2. And my first volume is 247 milliliters. And my second volume is my target. That's what we're trying to find out. What would be the final volume, right? And so then my first temperature, it says 22 degrees Celsius. We're not allowed to keep it that way. So we're going to add 273.15 and we get 298. 295.15. Yes?
Yes.
Okay. And then we take 98 degrees Celsius, which is nearly the boiling point of water, right? And add 273. So we can change Celsius to kelvins, and what do we get?
371.
371.15.
0.15.
Yep. Some of these smarties do all this math in their heads before I'm even done on my calculator with it, but I'm glad you're checking and got my back. All right, we're going to find V2. And so the easiest way I know to do this is to cross multiply. We'll just put our numbers into this proportion and cross multiply. What do you think?
Okay.
Will that work? Okay, so V1 is 247 milliliters. And T1 is 295.15 kelvins. And that's going to be equal to V2 divided by 371.15 kelvins. So V2 we solve by multiplying these two together and then divide by the third. When we do that, kelvins cancels away. And what do you get?
310.6.
And that will be in milliliters, it looks like, because I have milliliters here.
Right.
All right. Sig figs, we get to keep two sig figs. So instead of 310.6, we're just going to call this 310 milliliters. And let's see, does this make sense? Okay, so what did we do? The final volume, we heated up 247, so we expect that to expand.
Yes.
And that container got bigger because 310 is bigger than 247. All right, good. So we're getting something that makes sense. I feel like we could put a box around it now because we got what we needed. Let's do another example. There we go. Clear that old writing. Now we're going to find a temperature. At what temperature would 40.5 liters of a gas at 23.4 degrees Celsius have a volume 81.0 liters at constant pressure? So 40.5 liters, and then it changes to 81.0 liters, and then the temperature was 23.4 Celsius. So in kelvins, what's that going to be? 273.
$296.55.
Okay, so that's my first temperature. And then my second temperature matches my volume of 81 liters. So I'm going to cross multiply. V1 is 40.5 divided by T1, 296.55 kelvins. And that is equal to 81.0 liters over T2. Okay, so multiply across and then divide by the 40.5.
500 93.1.
Okay. And that's in kelvins, not Celsius, in case anybody was freaking out that that's a really high temperature. Remember, that's in kelvins. Plus, the volume doubled, right? So we expect it to get hotter. And it's almost twice as hot. Well, it is exactly twice as hot because they're directly proportional. So that's it. That's how we solve problems with Charles' law. Let's cruise through Avogadro's law. Avogadro's law, of course, we remember this guy Avogadro, right? He's talking about the amount of molecules, the number of molecules. He said that equal volumes of gases at the same temperature and pressure contain equal numbers of molecules. So his math worked out so that every time you had 22.4 liters of a gas at sea level and at standard temperature, then that equaled 6.022 times 10 to the 23rd particles, molecules. Oh, get that out of the way. So at a constant temperature and pressure, the volume of the gas is directly related to the number of moles. What if we put in more particles?
And the volume should increase.
Yeah, and that's what we saw before with our simulation, right? When we had more particles put in there, then it made our volume expand, right? So that's what we know to be true. Let's solve some problems using Avogadro's law. So, of course, we have a direct proportion, so we write our proportion constant this way, but what's our formula look like in chemistry? What do we use here? V1 over N1 is equal to V2 over N2, where N represents the number of moles for a gas. Oh, that's it. We don't have to do any examples. Nice. I like it. We'll probably have some in your homework, though. The Guy-Lussac law. Pressure and temperature are directly related at a constant volume. So I know I've talked to my students before about how to keep all of these laws straight. I don't care, really, if you know the name of which law is which, but some people do care. So if you don't want it to boil, you must keep the temperature constant. Does that make sense? And then we remember the Guy-Lussac law because it's terrible. The gay guy has no volume. That's just how they remembered it.
Interesting.
Yeah, but you know, anything you can relate to food or to sex, students remember. So the volume stays constant here, so volume doesn't get a feature in this equation. So we have pressure and temperature at constant volume means P1 over T1 equals P2 over T2. And then I didn't mention how to remember Charles' law because I don't have a snazzy way of remembering this. It's just the other one where pressure is constant. That's the only thing we haven't held constant yet. So that's how we remember which law is which. Pretty lame, but it works. So that's the Guy-Lussac law. Let's apply this. There's our proportion constant. Let the circle spin. Oh, I did the wrong escape. I love my edit button. Lets me edit out those mistakes. Okay, the combined gas law. Basically, we're saying we're going to combine some laws, right? So now, in this instance, the moles will remain constant. Otherwise, we won't be able to talk about what we need to talk about. So we'll take Boyles Law, P1 times V1 equals P2 times V2. There's Boyles Law. And then Charles' law has constant pressure, so V1 over T1 equals V2 over T2. And then the Guy-Lussac law we just talked about has pressure over temperature because volume is constant here. Oops, T. I said volume, and so I had to write volume. There we go, P1 over T1 equals P2 over T2. So these are our laws. You ready to combine them all together in the combined gas law?
Yes.
Alrighty, so P1 times V1 goes over T1, and then P2 times V2 goes over T2. Temperature's always on the bottom in these. Yep. So that's how we set it up, and that's why we always work in temperatures of kelvins, because we don't want to have zeros in our denominator. That will mess up our math. So that's our combined gas law, and now we're going to have some example problems. Yep, you betcha. Because you can always use the combined gas law for anything. Let's interpret this problem. A deodorant can has a volume of 175 milliliters. So the volume is 175 milliliters for our deodorant can. And a pressure is 3.8 atmospheres inside the can. 3.8 atmospheres. So it's pressurized. That's how it will come out when you push the little button. And then the temperature that's associated with that pressure and volume is 22 degrees Celsius. So normal room temperature, like if it's sitting on your bathroom shelf, right? So add 273 and we get 295. Okay, what would the pressure be? There's our target. So P2 is our target. What would the pressure be if the can was heated to 100 degrees Celsius? All right, so the can is still the same can, right? So we still have the same volume. Cans don't really expand and contract like a balloon does. And then the temperature is 100 degrees Celsius. So add 273 to 100.
373.
Yep. Without a calculator, like a genius.
You know it.
Yeah, so when our students are using their calculators for math like that, we're going to make fun of them because they deserve it. Here's our combined gas law. So we're solving for P2. Do you want to solve the equation first, or do you want to put numbers in and then solve? Do you have a preference?
Let's put the numbers in first.
Okay, might as well. So 3.8 atmospheres times V1, 175 milliliters. Then we'll divide by T1, 295.15 kelvins. And that's equal to P2 times 175 milliliters divided by 373.15 kelvins. Okay, if it's all the same to you, I'm just going to cancel this away since it's on both sides. Will that work? All right, so then I'm going to take 3.8 divided by 295. And then if I multiply by 373, I should be able to solve for the pressure. You got it?
4.8.
4.8 atmospheres. All right, so suppose that you took your deodorant can from your bathroom shelf and you packed it in your backpack because you know you have football practice today and you might need that stuff, right? But you left it sitting in your car all day and it got really hot that day, and inside your car that pressure is building up. Let's hope that the can is built out of some pretty sturdy stuff because the pressure increased by 1 entire atmosphere. So now instead of having 3.8 atmospheres, we've added the entire atmosphere of the Earth pushing out against the sides of that can.
Wow.
Yeah, wow, that's quite a lot of pressure. So maybe you shouldn't leave that sitting in your car. I'm going to leave the writing here because example 6 is dealing with this same question. So it says, what volume of gas could the can release at 22 degrees Celsius and 743 torr? We're going to push the little button and some deodorant is going to come out, and we want to know like how much space is it going to take up, right? Is it just going to be enough to cover your armpit, or is it going to fill up the whole locker room? So that's what we need to figure out here. And I wanted to leave the writing so we could see that all of these conditions for the initial conditions of our deodorant can are still true. Okay, the volume, the pressure, and the temperature. Did you write these down? And now our new conditions. We're going to find the new volume if we release some of this gas out of the can, and that would be a pressure of 743 torr. So we're not at sea level, or it would be 760, right? And the temperature is 22 degrees Celsius.
Which is the same.
295.15. So if you really wanted to go back to your old laws, when temperature is constant, then we'd be using Boyles Law to solve this problem. I'm going to go ahead and use the combined gas law. So 3.8 atmospheres is my P1, multiply by my V1, 175 milliliters, and then we divide by T1, 295.15 kelvins, and that's going to equal P2 times P2, so 743 torr. Heck, let's change that. 1 atmosphere is 760 torr.
.9776.
Okay, so that's my P2, 0.97, I'm going to call it 8 atmospheres. Why is my decimal point so high up? Getting all out of control. That's in atmospheres, and my V2 is what I'm trying to find out. And my temperature is still at 295.15 kelvins. So in my math, I can simplify this by getting rid of the temperature. And then to find V2, we multiply these together, right? And then divide by 0.978.
680 mils.
680 milliliters exactly? 680? Or do we have a whole bunch of numbers?
Oh.
No big deal.
Might good if I knew how to use a calculator. 680.2373.
Okay, so we've got all this calculator vomit to deal with. This is a measured value that's going to restrict how many sig figs we can keep. The pressure also is restricted to 2 sig figs. So we rounded this number after the 8. 680 rounds to, or 680.2373 rounds to 680 milliliters. And that's it. That's how we would use the combined gas law to solve a problem. And I believe that's the end of this podcast. Sure enough. Good, thanks for your help. See you guys later.
No problem.